ideal gas mixtures. We've solved some problems where there are mixtures of different components for ideal gases. And then we focus on the study of moist air and water vapor. And so that's the study of what we call psychrometric. And it's very practical, very important to mechanical engineers. In the study, we talked about dry air, which is a molar mass of dry air of 28.97 kilograms per kilomole. And you can think of it as 79% N2 and 21% on a molar basis O2, because those are the predominant components, and the next third and fourth most prominent component in air would be very small. It really drops off after the first two. And then if you start adding moisture to it, then you get moist air. And we talked about how to measure the amount of humidity in the air. We talked about both the relative humidity, phi, right? That phi is a Y of the vapor, so it's the mole fraction of the vapor in its current state divided by the maximum it could be if it was at the same temperature and pressure, but it would be saturated air. What would be the mole fraction of the vapor in saturated air at the same temperature and pressure? Well, that's convenient, but it's also, you can relate it to the partial pressure of the vapor in the current condition divided by its maximum partial pressure, which is its saturation pressure, Psat, at the same temperature. If you do get to be saturated air, that's when the relative humidity is equal to 100%. You can't hold any more. And a lot of times the temperature is increasing, decreasing. If you start to decrease the temperature, you may become saturated air. If the temperature drops any more because of cooling, then you dew out moisture out of the air. Okay. We also were introduced to humidity ratio omega, and we related it to the mass of the vapor to the mass of the dry air. So it has units of kilograms of vapor per kilogram of dry air. How do we calculate it? Typically 0.622, that's a ratio of the molar masses divided by the partial pressure of the vapor divided by the partial pressure of the dry air in the moist air mixture. So two humidities, relative humidity and humidity ratio. Let's solve this problem. A gas mixture has a molar analysis of 15% carbon dioxide, 60% nitrogen, and 25% water vapor. It's at a spanking hot temperature of 850 Kelvin, which is 577 degrees C. Very high temperature. And it's a total pressure of 1 atm. It flows through a heat exchanger where it's cooled so that it's now 350 Kelvin or 77 degrees C at 1 atm. So here's our heat exchanger. So there's some Q. I'm going to show it out, Q dot out, true. And we have either on a mass basis, you could talk about the mass flow rate or the molar flow rate. You could talk about the mass flow rate of each constituent, the molar flow rate of each constituent, where you'd sum I equal 1 to 3, I equal 1 to 3. And it comes in at temperature 1 and goes out at temperature 2. We always think about when you're cooling some air, you may want a drip pan in case there's some liquid condensate that may come out. True. So often you would put it like this. You would show a coil and a drip pan underneath the coil to catch any condensate. But in this case, the heat transfer is out of the air. It's being cooled. It's coming in at 850 Kelvin and it's going out at 350 Kelvin. How many degree change? 500 Kelvin degree change. How many degrees C change? Temperature difference. 500 degrees C temperature difference. True? So determine the inlet relative humidity. So we're asked for phi1. How would you calculate it? Either Y of the vapor at state 1 divided by Y sat at state 1. Okay, or you would calculate it by P of the vapor at state 1 divided by P sat at state 1. Okay, think about it for a minute. What is the partial pressure, PV? It's going to be Y sub V times P total. So it's 25% water vapor at 1 ATM. So it's 0.25 ATMs. And if you wanted to convert that, it's like 25, close enough with some change, kPa, 25 kPa. True? So that's what PV at 1 is. What is P sat at 1? How would you find it? Saturation pressure. Go to the tables. And you would look it up at what temperature? 577 degrees C. What do you think about being able to do that? Well, we want the saturation pressure for that temperature. Try Excel, sure, but you can use the tables as well. Interpolate, sure, but if anybody has a table, you want to whip it out and take a look. Anybody have that table? What do you say? What is the saturation pressure at 577 degrees C? Okay, what did you find about the P sat at 577 degrees C? Pardon? So you compare it to CP. TCP, what? Critical point temperature for water is 374 degrees C. That's the top of the dome. You can have steam at the pressure above 300 and temperature above 374 degrees C, right? But it's not going to, if you have a temperature above that, it's not going to change phase. So this is not defined. So what about the ratio to calculate relative humidity at state 1? Not defined. All right? That was probably the hardest question. How about now at the exit relative humidity? You want to phi2. You mean your relative humidity is going to be undefined on the inlet and it's going to be defined on the outlet? And so what we do is we say phi2 is equal to, and let's just assume it all stays vapor. It stays the same mole fraction. It's still 25.3 kPa coming out for the partial pressure because it comes out at 1 ATM as well. And it comes out at 77 degrees C. We look up 77 degrees C. You have to do a little interpolation in the table to get that saturation pressure. It's around 41.9 kilopascal. Does that look reasonable? Good. So we get a relative humidity on the outlet to be 59%. So it's if you continue to cool it, it'll probably get to the dew point temperature, and at the dew point temperature, relative humidity will be 100%, and if you cool it anymore, you're going to have the liquid coming out of that drain pan. True? But at this point, there's no threat of condensate draining off of that cooling coil. What about the heat transfer in kilojoules per kilogram of entering mixture? So this is like per m dot, true? How many kilojoules of heat transfer per kilogram of the inlet mixture? This is a long, tedious problem, but you approach it like you do all other long, tedious problems in thermo, is you introduce a nice system, the focus of the study, It's an open system because you have flow in and flow out around that cooling coil, and you have the rate of heat transfer coming into the system. I guess I want to change the direction of this so it's consistent with the way you typically write it, minus any shaft power out of the control volume, equal to m dot. It's what about the enthalpy? Exiting inlet, kinetic energy exit, kinetic energy inlet, potential energy exit, potential energy inlet, changes in potential, changes in kinetic, no work, all those are zero. So the equation that we have is that and also we have a sum of different i's, true, for each of those three components. Okay, so if you rewrite this Q dot N equal to m dot of the mixture times the sum of m dot i's over to m dot of the mixture is the mass fraction of each component times the change in the enthalpy. True? So Q dot N divided by m dot mixture equal to the sum of the mass fractions of each of those components times the change in enthalpy of each component. Well, we're given mole fractions, true? And you could work out to get mass fractions, true? I need to scroll down to find some more room. Can I scroll down? So we'll scroll down, and what we have is we have for the carbon dioxide, for the nitrogen, and for the water, we'll have the molar masses. You just kind of make the table like we've done before. This units of kilograms per kilomole. And it's 44.01 and 28.01 and 18.02. You convert from mole fractions to mass fractions. It's 23.7%. It's 60.2%, and it's 16.1%. So we have these mass fractions there. And think about state 2 going out, and I need enthalpy. All right. Couple ways to do this. If you wanted to, you could just replace this delta H by C sub P I T2 minus T1. But then you have to get the right specific heats. True? The average temperature is around 600 Kelvin. So if you could readily get the specific heats at 600 Kelvin, this may be the approach to go. This may be a good way to go. If I look at C sub P at 600 Kelvin for carbon dioxide, I think it's around 1.075. Same with nitrogen, 1.075. What about water vapor? Well, the water vapor, maybe the book makes it a lot harder to get a specific heat at a reasonable temperature like 600 Kelvin for water vapor. It can be done, but another way to do it is just to do it this way. I'm gonna use specific heats for the carbon dioxide and the nitrogen, and then I'm going to use H of G at state 2 and H of G at state 1 for the water, vapor. Okay, so if you take a look at the H of G coming in, it's for 3656, somewhere around there, kilojoules per kilogram. And then for going out at 77 degrees C, it's around 2641 kilojoules per kilogram. This one, it's the enthalpy of steam at a pressure and a temperature. This pressure is 0.25 bar or ATM, 0.253 bar or 25.3 kilopascal, and the temperature coming in was 577 degrees C. So when I put a G there, that's a misnomer, right? It's just the enthalpy of the vapor at the superheated state of the temperature and pressure. It's partial pressure and it's temperature. This one, H of G of 2, it is the enthalpy of saturated vapor at that temperature of 77 degrees C. Well, so those are all the pieces of the puzzle. So you would slug through it and put a Q dot N divided by M dot of the mixture is equal to the first mole fraction, 0.237. And you know what? Because these are the same, just add them up. True? Not the mole fractions, the mass fractions. So if you just add that up, that's 0.93. So it's 83.9% times the specific heat, 1.075 kilojoules per kilogram Kelvin, times a 500 Kelvin temperature change. True? That accounts for the CO2 and the nitrogen. And then you have the rest of it, 16.1% times the difference in the enthalpies going, I just realized that both of them are going to be heat removal, so I need to probably put a negative on that temperature. So it's going to be a negative Q dot N, and it'll be 2641 minus 365.6 kilojoules per kilogram. And the final answer, Q dot N per M dot, comes right at 615 kilojoules per kilogram. Make sense? You follow that? All right, ready for another problem? Here we have moist air at 80 degrees C and 400 kilopascal and 40% relative humidity. It's contained in a 2.5 cubic meter closed rigid tank. If the tank contents are cooled to 60 degrees C, determine the final pressure in the tank in kilopascal. So we want to find, let's say, P2, the final relative humidity, phi2, the final humidity ratio, omega 2, and the heat transfer during the process in kilojoules, Q1 to 2. So we have a rigid tank, and it's at state 1, and it undergoes cooling to state 2. So here we don't have an open system analysis, we have a closed system, true? So think of that as a closed, and you need to step through the problem in a couple of incremental steps. If I start at 400 kilopascal and the contents are cooled from 80 degrees C to 60 degrees C, what do we think P2 should be in relationship to 400 kilopascal? Greater than 400, equal to 400, or less than 400? We have a vote for less. It's a rigid tank, and the contents are ideal gases, and it's being cooled. It's going to be what? Yeah, it'll be less. Now, if they're all ideal gases and they all stay as an ideal gas, then can you use the equation something like, oh, PV is equal to N R bar T, the total number of moles stays the same, gas constant stays the same, the volume stays the same, and so the final pressure over the final temperature is equal to the initial pressure over the initial temperature. So the final pressure is P1 times T2 over T1. So you can do that, and it starts out at 400 kPa, and it's 80 to begin with. That's 353 Kelvin, and it's 60 to end with, 333 Kelvin. And so you can calculate the final pressure, assuming that all of the water vapor stays in the vapor state. It behaves as an ideal gas. Yep, let's do this. Let's find you can do that or check the relative humidity, okay? If the relative humidity is less than 100%, then you didn't get as cold, as low as the dew point. All right. So what about Phi2? Is that going to be the vapor pressure at 2 divided by the saturation at 60 degrees C? That seem reasonable? Okay. How do I calculate the vapor pressure at 2? How do I calculate PV at 2? If I knew the mole fraction of the vapor and I multiplied by P2, which we just calculated to be 377.3 kPa, forgot to finish out the answer there, then wouldn't that give me PV at 2? So I got to get the mole fraction, all right, and the mole fraction of the vapor at 2. Is that equal to the mole fraction of the vapor at 1 if none condensed? It is. How do I calculate the mole fraction? The mole fraction of the vapor at state 1, because it's 40% relative humidity, is that going to be the PV at 1 divided by Psat at 1? What is Psat at 80 degrees C? The saturation pressure at 80 degrees C is 47.39 kPa. What is the relative humidity? Phi is 40%, and so PV is equal to Phi times Psat. That's what I was doing wrong. This is relative humidity at 1. Okay, so it's 0.4 times 47.39 kPa, and so the saturation, the partial pressure of the vapor at state 1 is 19 kPa. All right? All right. Now, what is the mole fraction of the vapor at state 1? Is the mole fraction of the vapor at state 1 equal to the vapor pressure at state 1 divided by the total pressure? So it's 19.0 divided by 400 kPa. True? Okay. Now, the mole fraction stays the same because you're not going to be condensing. The total pressure is going down. It went from 400 to 377 kilopascal. But the mole fractions stay the same. And so we can calculate the partial pressure of the vapor at state 2. That's going to be the mole fraction of the vapor at 2 times the total pressure at 2, which is 19 over 400 times 377.3. So we find the pressure, the partial pressure of the vapor at state 2 to be 17.9. And we compare that to the saturation pressure at 60 degrees C, which is 19.94. And we get phi2 is equal to right at 90% relative humidity. That's a lot of work to get that the relative humidity went from 40% to 90%, but nothing condensed. Nothing condensed. True? I'm sorry? Well, we're going to solve this again at a lower temperature, and then I'll show you how it has to condense. But, well, you make that assumption, and if you calculate the relative humidity that's less than 100%, you're good, because you're assuming everything stays in the vapor state. Relative humidity is less than 100%. Okay? All right. What is the final humidity ratio, omega 2? How do we calculate that, omega 2? Is that 0.622 times the vapor pressure final divided by the dry air final? Is that the equation? Sure. So 0.622. What about the vapor pressure? We just calculated that. That's 17.9. And then the difference between 377.3 and 17.9 is the partial pressure associated with the dry air. And you get a humidity ratio at state 2 to be 0.0309 kilograms of vapor per kilogram of dry air. All right, that's part C. Now, part D. What is the heat transfer during the cooling process? And I need more room, don't I? So, if you allow me, I'm going to scoot down and I'm going to write a first law for this control closed mass, this system. So if I write the first law, and we'll put Q1 to 2 in, Q1 to 2 into the system, minus work 1 to 2 out, equal to cap U, final minus cap U initial. True? There's no work because it's a rigid container. And now what we have that the Q1 to 2 that goes into the system, we expect that to be a negative quantity because it's not into the system that it's coming out. We'll do it as a sum of 2. So we have the mass of the dry air times the change in the internal energy of the dry air plus the mass of the vapor, the change in the internal energy of the vapor. All right. What about the mass of the dry air? We can calculate that. We know the partial pressure of the dry air to begin with. So you calculate that to be 9.403 kilograms. All right, so the mass of the dry air, just using the ideal gas law, is calculatable. If you want to multiply by the specific heat constant volume for the dry air, then the temperature change, T2 minus T1, that's pretty straightforward because the specific heats don't change that dramatically between 80 degrees C and 60 degrees C. You can get a good constant value for that. And the specific heat typically 0.72 kilojoules per kilogram Kelvin for the dry air. And then this was 60 minus 80 Kelvin or degrees C, they cancel, temperature change, and then 9.403 kilograms. So that's how you calculate the amount of energy required or heat transfer required to reduce the dry air temperature from 80 to 60. You calculate the same type of equation. The mass of the vapor is equal to the pressure of the vapor, the total volume of the tank, molar mass of the vapor divided by R bar T to get the mass of the vapor, just like for the mass of the dry air. That one, we come in at 0.291 kilograms. Now you're left with a choice: look for a specific heat or just use the tables. It would be 0.291 use of G at 60 minus use of G at 80. So saturated vapors internal energy at 60 degrees C and at 80 degrees C. Let me do this. 0.291. What is U of 60? 2456.6 minus 2482.2 kilojoules per kilogram. All right. When you finally compute this, what we have is negative 143 kilojoules. 1 to 2 in. So that takes it from 80 degrees C to 60 degrees C. The relative humidity at the end of the process was not 100%. The relative humidity was right at 90%. So it's getting close to being saturated. All right. So now I'll continue the problem. I'll click to another slide, but try and remember about a negative 150 kilojoules. In this problem, start with the same air, the same container, and this time you cool it not to 60 degrees C, but you cool it to 40 degrees C. And you do the same type of thing. You have to march through and calculate all of these values. Let me give you a quick synopsis though. We went from 80 degrees C to 60 degrees C, and Q was negative 143 kilojoules, right? If you go from 80 to 40, what do you think? Negative 300, a little more than double. But the thing is some of that is going to condense. Okay, and when it condenses, there's a lot more energy that needs to be removed to condense water vapor. To cool water vapor is one thing, to condense it's another. And the final answer, to help put it in perspective, is negative 655 kilojoules. That's a lot more than just double. So how do you make that calculation? Let me just give you kind of working backwards here. Q1 to 2 will be the mass of the vapor, specific heat, constant volume, not the vapor, the dry air, sorry, of the dry air. And then the temperature difference, okay, the delta T, which is the final temperature minus the initial temperature. And so this is roughly double what we had before. I mean, it's just a temperature, it is double what we had before, because the temperature difference used to be 20 degrees C, now it's a delta T of 40 degrees C for the dry air. But you bust the water into two considerations. You have to find out how much liquefies, how much is now liquid at state 2, and how much remains vapor at state 2. And then you have use of G at state 2 minus use of G at state 1. But for the liquid, we have use of F at state 2 versus use of G at state 1. And the use of F is 167.56 kilojoules per kilogram at the temperature of 40 degrees. And use of G at state 1 was 2482.2. This is a big difference. The change in internal energy is very large when you have vapor to liquid at a lower temperature. You've condensed it. These things change just a little bit. Let me show you the numbers here. Use of G at 2 is 2430.1, and use of G at 1 is 2482.2. So we have to really, to do the energy balance correctly, we have to find out how much of that mass condenses. And so what you can do is you could act as if it none condensed, then you would calculate something like the relative humidity at the final state would be over 100%. So you'd have to backtrack. Here, just assume that the air is saturated air. It's saturated air at the 40 degrees C, okay? So if it's saturated air, what's the partial pressure of the vapor? It's going to be Psat. It's going to be the saturation pressure at 40 degrees C, true? So the saturation pressure is 7.384 kilopascals. Okay? You can now calculate the mass that's in the vapor state. Is that the vapor pressure, total volume, molar mass of the vapor divided by R bar T? And you find it 0.1278 kilograms. So this is at the ending, at the 40 degrees C. But we started with, in the vapor, 0.291 kilograms. So the difference is the mass that is now liquid at state 2. So the mass that's liquid at state 2 is 0.163 kilograms. Quite a bit. Quite a bit was the liquid. How much volume does that liquid occupy? The volume of the liquid is the specific volume times the mass of the liquid. This number, 0.00100 something, ... you get very small volume. So you don't even really need to make the correction for the tank is here, and I have now a little bit of liquid condensate on the bottom. And now the vapor doesn't really occupy a full 2.5 cubic meters. It occupies 2.5 minus the volume of the liquid. You'll just be chasing the sixth digit, okay? It won't be worth it. But you see that you get some significant amount of mass that is now liquid, and the vapor at state 2 is 0.17, this number is 0.1278 kilograms. This number is 0.163 kilograms. All right. What about the final pressure in the tank? Well, you know that the mass of the dry air didn't change, true? What was the mass of the dry air? 9.403. Okay. The partial pressure of the dry air times the volume of the tank times the molar mass of the dry air is equal to the mass of the dry air times R bar T. So you can calculate using the ideal gas equation that partial pressure of the dry air at state 2. This is T2. And you calculate the partial pressure of the dry air is 337.9 kPa. So you add that to the 7.38 kPa for the partial pressure of the water vapor to get the total pressure. And the total pressure of the tank then is, what is that, 345 kPa. So that's the answer to part A. You almost work backwards a little bit. You don't have to. I wanted to really emphasize the answer to part D for this problem because that's the significant change, how much heat, extra heat transfer there is because you now condense some of the vapor. All right. Final relative humidity, 100%, true? And then final humidity ratio, what is that? So the final humidity ratio, omega 2, is what is the mass that's in the vapor state divided by the mass of the dry air. 0.1278 divided by the mass of the dry air, 9.403. And you find omega 2 to be 0.0136. These are tough problems, aren't they? Just work through them carefully.
Why on this one was it split into, how do you know to split it into vapor and liquid?
Well, in a way, what you can do is go back and start with this approach right here. Just say, okay, I'm going to assume it goes to 40. I'm going to assume it all stays vapor. And what you're going to find is that phi of 2 is well over 100%. Then I have to back up. I can't have relative humidity over 100%. It's now saturated air. How much was condensed? I have to work at that. But that's the way I would go, is find what phi is, assuming everything stays vapor. Well over 100%, I have to back up. Somebody else have a question or comment?